Welcome to the third session of the first week of the AI lecture series. So, in this session, we will be exploring some of the topics that we are going to cover throughout this class. And I'll be giving a short introduction um, with the hope that you will find these topics interesting, and also you may get an idea of what kind of mathematical and programming background you may need to brush up to in the coming weeks. So, all right, let's go and see what we have. So, first we have supervised learning. So, this is where we tell AI, or I'll use the word computer here. So, we'll be telling the computer, so this is how it should be done, or we are giving it information and we are helping it learn, and then afterwards it is able to make decisions on its own. So in this example given, like we show the computer different apples and say also like these are apples, or this is how apples look like. And when we actually give them an apple later, the computer will be able to recognize that this is an apple. So this is a very basic scenario, but this is the premise of supervised learning, which we will be starting from next week. Then one of the first things in supervised learning would be learning linear models. So we'll be looking at our data, and we'll be trying to create a linear model. Like it could look like something that you are very much familiar with, y equals mx plus c. Sorry, I might make myself a little bit smaller. So this could look like a straight line, or it could be a polynomial as well, as you can see in this picture. It could be a polynomial, but we'll be mainly looking at just straight line, and we'll also talk about how different distributions of data, as you can see here in this area, like some data distributions, like this example, it works really well, but some of them don't work that well at all. So we'll be looking at these things and the complexities around linear models, and we will be coding a linear model as well. So from next week onwards, we'll be actually doing some coding, hands-on practicing with these concepts. So you will probably need to brush up your linear algebra skills as well as your coding skills in whichever programming language it might be. So I will probably be doing my examples in either Python or Julia, but you are welcome to follow along with any programming language. Then we'll look at logistic regression, where we use a logistic function to make better decisions. So we'll cover this later when we actually come up to doing this part, but I just wanted to mention it here as well. And after that, we come to an exciting topic, which is parameter estimation. So the earlier part, where we talked about linear models and logistic models, we are talking about scenarios where we can see independent and dependent variables. But what about when we just have observations? So maybe you have heard of this concept called hill climbing, or gradient descent. So basically, imagine this is a map, and I'm sure you have seen maps where you have the height marked similar to this. So imagine someplace here, then you know that this, if you go this way, then you are climbing down, and if you go this way, you are climbing up. So this is a problem where we have a solution space. So this whole thing is our solution space, and what we want to do is we want to find the peak with the maximum value and find the parameters. So we have two parameters here, the two parameters which should give us the maximum value. So in this case, I think this is our maximum value. So what we are interested is doing what we are interested in doing is to find x for parameter 2 and y for parameter 1, such that the function of parameter 1 and parameter 2 is maximized. So this is what we'll be doing for parameter estimation. Again, a little bit of linear algebra would come in quite handy here. Alright, then we'll be looking at decision trees. This involves us looking at how to make a decision. So I have used a simple example on how to decide what to do on a weekend. Is it raining? If yes, we are not going to go anywhere, we are going to stay in. And is the internet working? Because sometimes when it rains, internet might not work. So if internet is working, we can watch Netflix. If not, we can read a book. Similarly, we have not raining scenario as well, where the options are go to the mall or go to the beach. So here what we have is an example of a model decision tree, and using this, given the background or given the environmental situation, we can come to a conclusion on what will happen. If we give something like this to the computer, it will not be able to come up with the decision tree by its own, but once there is a decision tree, it should be able to make quite good guesses. So let's say so what's Rajit doing this weekend? And the computer will go and say, oh, is it raining? Okay, no, it's not raining. Is it too hot? It's not that hot either. Okay, so then he's probably at the beach. So this is a basic idea. And then we have random forest. So what is a forest? So a forest, we say for the context of this subject, is a collection of trees. So a forest is a collection of trees. So a random forest is a collection of decision trees. So here we have the same decision tree, but these could be different decision trees, and these decision trees may have different configurations, and they may come up with different outputs. And then we'll look at all these different decision trees and see, okay, what do most of these decision trees think will happen, and we can go with the consensus result, or we can use some kind of a probability calculation to see, okay, so most of the decision trees are saying that this will happen, but there's this one decision tree which insists on this other option happening. So we can get a more informed decision, or the computer can come up with a more informed decision by using random forest approach as opposed to a single decision tree. And we talked about supervised learning. What about unsupervised learning? So I thought I should mention that this illustration, I really liked it. It's from this book called The Wild Robot. So the idea is we let the computer figure out things on its own. So for example, let's say there's apples. So let's see if I can draw some apples nicely. Okay, this is an apple, this is an apple, this is again an apple, and then let's say we have bananas. Okay, I might use a different color. Okay, I apologize for my banana drawing skills, but say we have apples and bananas, right? And then we just show this to the computer. So what the computer will do is it will look at the data presented and find out characteristics about the information given, and it will be able to say, okay, these look like it's the same type, and this again look like it's a different type. So it will tell us this is type 2 and this is type 1. So this won't tell us whether they are apples or not, but it will tell us, okay, these are type 1 and these are type 2. And maybe like we'll introduce a tomato, and it will think it's a type 1, which is an apple. Or maybe we'll introduce something that looks like a banana. Maybe we'll introduce a cucumber, and it will think it's a banana. But the idea is that it is able to figure out by its own, like, what are these differences, and maybe it's able to categorize these things, not necessarily know what it is, but knowing that there are these two types of things. So hope that makes a little bit of sense, but we'll be exploring this topic in more detail as we go on. So then we have as part of unsupervised learning, I think that's what I sort of described earlier, we have clustering. So I wanted to show this example, a very popular example, which we will be working on, is on identifying two different colors of the iris flower. So we have these, three different kinds. So we have these three different varieties of the iris flower, and we have four features of the flower. So we have the sepal, which is this part here, and the petal. So each of the flowers have sepals and petals, right? And we know the length of the sepal and the length of the petal, and similarly we know the widths as well. And can we, by analyzing these features, cluster the three different types of flowers separately? So this is what we are going to look at. We will be looking at different clustering techniques, etc. And coming to a very interesting topic, we'll be looking at emergent learning, or what we call evolutionary learning. So we know that humans evolved from apes, right, as you can see here. And can we evolve our solutions to be more intelligent, or can we evolve our solution to be more efficient as we go along generations? And turns out, yes. So we have this spacecraft antenna developed by NASA using a similar approach. So as you can see, like the first generation is a more simpler shape, and through evolutionary learning or emergent learning, it had come up with this really weird shape, which is not intuitive at all. But using genetic programming, we can come up with solutions that are not intuitive to the human mind. So this is a very interesting aspect of artificial learning, especially for me personally. And we'll be looking at emergent learning, and we will be coding some genetic algorithm examples as well. And then we'll be looking at swarm intelligence, which is where, like, maybe you have seen swarms of bees, or like murmuration of birds, where like there's no specific leader, but all these individual birds or individual bees are communicating with those around them, and as a result, the whole bee colony or the whole the group of birds, they come up with something intelligent, or like they come up with a pattern or a behavior that is useful to all of them as a whole. So this is what we call swarm intelligence, where the individual agents we call, like each bee or each bird, we call them an agent, where individual agents work with those around them, and they are not aware of the big picture, but because of their collaboration, the overall result is a favorable one. So this is what we call swarm intelligence, and you can see that like humans also sort of engage in swarm intelligence behaviors. I will talk about these things, and also code an example of swarm intelligence as we go on in the lecture series. And as the last part of our programming exercises, we will talk about neural intelligence, where we'll be looking at how humans have tried to approximate a neuron in computers, or like programmatically approach a neuron, and how we use these neurons to create neural networks which are by far like very intelligent, and they could be trained to do really interesting things. So we'll be looking at normal neural networks, then deep learning with deep neural networks, recurrent neural networks, maybe long short term memory networks. So there would be some really nice applications. So maybe you have seen those programs that can look at pictures of cats and dogs and identify what are the cats and what are the dogs. So we'll be looking at some of these things, and probably we'll look at how to identify handwriting using neural networks. So yeah, so this is a picture of what's to come, and I hope you guys are interested to learn these topics, and we'll be doing some simple coding exercises as well. So yeah, like for neural intelligence, we'll be spending about 2 weeks, and I think that should take us to the end of the semester as well. So what's next for next week? Okay, so sorry, I think my device got disconnected. Let me come back. So sorry, that's all right. It doesn't matter too much. So what's going to happen next week is we'll be looking at linear models. And all right, hope to see you with the linear models, and have a good week.